All right, welcome everybody to the April 2022 San Jose Astronomical Association imaging meeting. And today we have Nikola Nikolov, who's going to talk to us about astroimaging and photometry with your amateur backyard rigs. So take it away, Nikola.
Yeah, thank you so much. Hi. Today I'd like to actually talk a bit of a small experiment that I have been doing in the last year and a half. I'm also very passionate in the astrophotography in general and pre-processing the data, making pretty pictures of the deep sky. But one of the problems that we all face as astrophotographers imagers is that we live in very light polluted areas, right? And living in such light polluted areas causes a lot of limitations of what we can take image of, right? If you have been actually following the SIG meetings and Astroimaging group in SJAA, probably learn what are the techniques that are mostly popular for imaging from city skies and light polluted areas. So we have continuous trend of increased light pollutions in cities, right? Because the cities are growing, right? And people need to actually install more and more LEDs and the street lights. They don't care about the light pollution. And that causes a big issue, not only for amateur astronomers, but also for professional astronomers, especially at Lick Observatory, because it actually, the light pollution limits what can be done strongly. Currently, if you live in Bay Area and you want really to actually see the starry night clearly and you want to see the Milky Way in summer, you need to drive at least 2 hours from Bay Area. So the nearest location that you can see really clearly the Milky Way is 2 hours from here. And as we increase the light pollution, it's getting worse because we have to drive more than 2 hours, 3 hours to the mountains to see these beautiful views. For professional astronomers and astrophotography, limitations are that we can image and investigate specific objects. Of course, if you live in a very, very light polluted area, you can actually image the sun, right, with the solar telescope, the moon, which is very bright, some few bright planets. And the recent technology in astrophotography, amateur astrophotography, allows us to image Emission nebula with narrowband filters. And that's pretty much it, right? If you live in these light polluted areas. And one of the questions that I have been kind of curious is what else can be done? What else can be seen from these light polluted areas if you have certain equipment to do that? So this is an example of what the light pollution sky looks like in the emission spectrum, basically. So this is actually a real data set, real spectrum measured in Vienna, Austria in 2018. And it actually represents the relative irradiance intensity of the light in the sky versus the wavelength. And what you can see is that you see this kind of bell-shaped spectrum, which is centered around there between 550 nanometer up to 620 nanometer wavelength. So that shows you that actually light pollution is very spread in different wavelengths, but it's mostly within the area of yellow wavelengths, basically green or yellowish light. And this is actually used by both professional astronomers and astrophotographers to actually use specific filters and cut off that part of the spectrum. And we can focus on those parts of the spectrum that are actually related with even emission nebula or specific other objects that we want to see. And these two areas are even higher with lower wavelength, which means we're going to UV or shorter wavelength, or we can go into higher wavelength, means we go to red or infrared spectrum. Yeah. And the dots are actually the data, and the simulation is in the blue area, means that simulation and experiment, they fit pretty much well. And on top of it, when we live in light polluted areas, the situation is getting even worse if we have full moon, right? Full moon nights, light polluted area for astrophotography is the worst case scenario. So here's the spectrum of the moon, the emission spectrum of the moon. This is from Colorado State University. And it shows actually for different phases of the moon, what is the radiance from the moon, for the reflection. And what we see that is actually the spectrum is very steep and quickly going down into shorter wavelength, means that for blue light and more like near UV, ultraviolet, the intensity is going down pretty quickly. And then the intensity is actually decreasing, but slowly when we go to bigger wavelengths than into red and infrared spectrum. But again, the centroid is actually located near the yellowish color, greenish color. This is also good news because one can be design filters which cut off this part of the spectrum, and we can image objects in the deep sky which are outside this yellow area of the spectrum. And this is the case with the emission nebula. So emission nebula use so-called narrow band filters, and if you follow the next actually SIG meeting, Francesco, who is one of our members, this is an example of one of his images recently with narrow band filters of the Rosetta Nebula. So, and this image is actually, the data are collected from San Jose area, right, from the Bay Area. But to get this image, he uses 3 filters, right? Narrow band filters, which are oxygen 3, which is around 500 nanometer. Then hydrogen alpha, or TH alpha, which is 660 nanometer, right? And silicon sulfur 2, which is the second filter. So both these 2 filters are red, and this one, oxygen 3, is green. But by using stacking softwares like PixInsight, we can create artificial colors of each filter in RGB, and we can actually stack them together. And you can see, you can actually create a colorful picture like this of the nebula, right? But this is just one kind of objects that we can actually take image of, right? So this is specifically for emission nebula, and not all the time around the year we have access to emission nebula on the sky, like the current season, because current season is mostly galaxies, and the galaxies are not very responsive to narrow band filters. So they're not. So if you use narrow band filters, you can see the galaxy, but you cannot get pretty images. And this is the case where basically, if you want to take pictures of faint objects like galaxies or dusty clouds in the sky, deep sky, basically you need a different technique, different set of filters called LRGB, right? These are 4 filters. We also, which actually, when you stack the images together, you get a colorful image, but you cannot use this technique from city sky, from light polluted area. So basically, if you want to use LRGB filters, you have to take your car, drive 2 hours from here, and I can collect this data and make pictures like this. So this is actually image of a reflection nebula from Australia. I actually collected the data, but the location in Australia is very remote and very far away from cities. That's why the image is so good, because there's minimum light pollution in this area of Australia, so to get this data. And such kind of image is impossible to be actually generated with data from city sky, right? So these are the two major techniques that are currently used for astroimaging photography. And so if you look at where these filters actually are located, so all the filters that we use for astroimaging, they're into the visible wavelengths of the spectrum, basically visible light, right? That's why we can actually make these colorful pictures, because they are close to what our eyes can see as a natural colors. So, however, there are other kind of filters which are called photometric filters, and they're used mostly in scientific astrophotography and also used into photometry in general for different reasons, mostly for scientific reasons, but also for calibration of telescopes, right? Calibration of the optics, or we want to sometimes measure the sensitivity of the camera or some parameters of the cameras that we use. So we use these photometric filters to do measurements. So these filters are not for getting colorful pictures, but for data, basically collecting numbers. And we use these numbers for different things. So these photometric filters, they cover much wider range of wavelengths, from ultraviolet to mid-infrared, and including the visible spectrum. And they have different
Nikola, I can't hear you. Can you hear me?
which seems to be accessible from city sky. So in specific conditions. And I haven't explored the near UV yet, but it's also interesting. And maybe in future I can try that as well. So for the metric filters that are used in the scientific astronomy, they're actually published online. And this is the naming convention. It starts with U, B, G, V, R, which are, this is for ultraviolet. Then we have 4 filters for visible light, B, G, V, and R. I know that V stands for Vega, because this is the part of the spectrum which is actually matching the Vega star in on the sky, and this is the wavelength which is corresponding to that star, 551 nanometer. That's why it's yellow, right? Red, which is very close to H alpha, right? This kind of region. And then we have a bunch of filters in infrared, starting with I, Z, and all this set of filters. And you can see that the wavelength is actually between 800 and 6 nanometer up to 3 microns, right? This is almost 3.5 microns wavelength. And then it goes even further with mid-infrared, where the wavelength is actually up to 21 microns. And so when you look at these filters, they cover so wide area. And for this reason, basically, the cameras that are mostly used for these filters are CD cameras, because CD cameras have sensitivity which covers wider range of wavelengths. So they're pretty suitable for photometry. I haven't heard if somebody has tried this kind of filters with CMOS, but I'm curious what will be the result. Recently, I actually bought a CMOS camera, ZWO, and I will also experiment with one of these filters, or a couple of filters, to see what will be the result. But typically, astronomers use CCD cameras with this set of filters. So the difference with the astrophotography filters is that the main purpose is measurement of the energy fluxes and magnitude of the deep sky targets. Images are grayscale. They're not colorful, so they're kind of boring, but they contain very useful information and useful data. That's the value, right? It's not about the color pictures. So they cover much bigger wavelength ranges. So in astronomy, the color of an object is actually a number. It's a float number. It's not actually, you can't tell the color of the object like a red, blue, green, but there is a metric scale. And based on that, astronomers can tell whether the star is more bluish or more greenish or more yellowish. But for different wavelengths, there are different details from the stars and galaxies that are interesting in these different regions. And that's why people use these filters to see these details. These are not narrow band filters, they're actually wide band, but in much bigger, away from the visible spectrum, right? And they're also available for purchase. Basically, if you go to High Point Scientific or OPT retailers, they're available. They're roughly the same price as normal filters. Sometimes could be a little bit more expensive. But in general, for the same cost that you spend for narrow band filters, you can actually have a full set of photometric filters, and you can start do something interesting with them. So currently I have only I, because I accidentally somehow discovered that with I can actually see something interesting on the sky with my telescope in the image. But I plan also to buy the Z filter because it's actually, it will push my rig even further in near infrared spectrum. I'm not sure if the others are available, but from the Astrodon set, it has I and Z that are available. All these visible filters are available too, and the U filter is, I think, available, right? The others are, I think, not yet available. So if you go to Astrodon webpage, this is how the transmission spectrum looks like. It's a bit blurred, the graph, but you see all the filters with different colors and what are the wavelengths there they cover. As I mentioned, these are wide band filters, so they cover much larger portion of the spectrum than the narrow band. And today we'll focus mostly on I and Z filters, and I can show you how the deep sky looks like with these filters and what are the surprises. And that will be interesting part of this talk. Meanwhile, if you have any question, just let me know. I talk sometimes more be too fast.
I had a quick question. So
yeah.
I know the atmosphere blocks a lot of the longer wavelengths, like the water and the air, but these are selected so that they pass through the atmosphere?
Yes, they pass. They pass. And also what I found is that sometimes they require actually large exposure time. Let's say they're larger exposure time than O3, ocean 3. But they actually have enough transmissivity to actually see the object on the image. Yeah, so I haven't tried with Z yet, but I filter definitely gets good images. You can see the galaxies and other objects as well. So I have today two kinds of objects, galaxies and some interesting stars with these filters. I will start with, yeah, do you have more questions?
Yeah, I have a question.
Yeah.
Back on the spectrum of light pollution, it showed that the light pollution was strongest in the yellow-green area. That's exactly where the human eye is most sensitive also. Is there some feedback? Is this data feedback with respect to human perception, or is that just a happy coincidence, as it were?
It's not coincidence. Actually, this is the reason why light pollution is bad for us, because it actually interrupts our sleep hours, especially when the weather is cloudy and the reflection of the light pollution hits the clouds and reflects backward, and it interrupts our natural need of sleep. So it's not coincidence. Yeah, and our eyes are mostly sensitive to green light.
Mm-hmm.
Yeah, and also not only us, but also the birds and other wildlife creatures. They're confused by all this light pollution. Yeah.
Sorry, Nicola. Your chart show that up to the 700 nanometer, and instead the filter you are using are 800 and more. So
Yes.
that means that 800 and more, the pollution is low or close to zero?
Yeah, so if you look at the light pollution spectrum, so we are, when I use eye filter, we are beyond 700 nanometers. So we are always in the very right end of the light pollution spectrum. So it's, yeah, close to zero, but we still see residual from moonlight, right? Because moonlight, if it's full moonlight, is the radiance is still not zero, right? But if you point the telescope not close to the moon, you still get decent image of the galaxies and the objects, right?
Sorry, the max, mean, and mean are the difference between max and mean are the distance from the moon.
Yeah, well, this is like I need to check that. Let's see. I think this could be. Yeah, this is. I can check whether this is 95% or I mean, mean and max around the mean, and I can tell you what exactly is this. Yeah, so this is probably the maximum intensity of the light that you get from the moon, because it could vary from where the moon is on the sky, what angle it is, right, and versus the atmosphere, right, and also other things which are can impact the light.
Yeah, distance of the moon from the Earth.
Yes, yes. So this varies, but I can check whether this includes 95% around the mean. Yeah. Okay.
So I have a question, observation. As you get into the infrared deeper and deeper, is it not so that the amount of water vapor in the atmosphere will drastically cut down the amount of infrared that can reach your observing position?
Yeah, yeah. So that's true. Yeah, but I haven't actually tried with really far away near infrared filters yet. I'm still into the 800 nanometer range, which is at least not impacted so much by the white vapor for now. But all these filters below, they could be impacted, but I haven't tried yet.
Okay, thank you.
Yeah. Then they're also not available, not all of them. Right? Yeah. So I can show you one example, which is with the famous Forehead Nebula, IC 434. Right. And this example is actually from Symbiotic, from Alden, the famous database. So on the left is the image of Horsehead Nebula with visible wavelength. And this is the image that we like to see with the nebula and the dusty regions around and all the the colors, right? And on the right is the same part of the sky, the same object, but with 2 microns wavelength. Right? This is the famous 2-mass telescope, which actually collected data in the past. And what you can see is that when you go to 2 microns wavelength, essentially the nebula is gone, right? You can see a little bit of the silhouette of the nebula, but most of it is gone. And what is the surprise is that in this region where the dark dusty region is kind of looks like nothing is there, all of a sudden you see a star here, right? And this star is not visible on the left image. And that is one of the reasons why astronomers use infrared imaging, is that they like nebulas and dusty regions, but sometimes they want to measure hidden objects behind the nebula or inside the nebula itself. And when you go to this long wavelength, they actually have access to these hidden objects. And in the next example, I will show you a more drastic example of that with one of the famous galaxy clusters on the sky, which is actually not visible from northern hemisphere, but southern hemisphere. So why astronomers need to remove nebula and dust from the images, right? This is an image of normal galaxy cluster, which is actually, I made it specially, took these images for today's talk. So I posted the image, the final result on Astrobeam. And this image is actually a stack of data from my telescope. I use actually a RASA system, specifically because I wanted to capture the star field of normal galaxy cluster, because the galaxy cluster is actually hidden inside the Milky Way galactic plane. And this is the result after 1 hour of data. You see countless number of stars, and you cannot really recognize where is the galaxy cluster, but it's here, right? So I know because I plate solve the result, and I know where the galaxy cluster is. So these dots that look like stars are actually galaxies, and there are more galaxies on the image, but they're basically obscured from the star field. And this area of the sky is also known as the great attractor, because there is a strong gravitational field which pulls all galaxies in this galaxy cluster in one direction. There's no known root cause yet what causes the great attractor, but the access to the great attractor is obscured by so-called zone of avoidance, because this galaxy cluster is basically behind our Milky Way galactic plane. And if astronomers have to do research of this galaxy cluster, obviously they have to remove all the stars, right? But astronomers cannot use star reduction algorithms, methods from PixInsight, right? Because if you use PixInsight to do star reduction, it will remove everything, including the galaxies, because it will consider these dots as galaxies, right? So what they do, so there are different techniques, but I can show you what is the result if you switch. This is invisible wavelength. Let's switch to infrared, right? And this is the same part of the sky. I a little bit zoom a bit this in the center of the image, this region, but in near infrared. So I use also eye telescope because it's not accessible from here. And now we see much less number of stars and things which are more likely like a galaxy, right? This is really a galaxy, right? Another galaxy here, another galaxy here, more here, right? You start seeing details of this galaxy cluster in a much better way than this way, right? So so when we switch to near infrared, because you can see remove big portion of the star field and the dust and actually see through it, and you can see these distant galaxies that are there, right? And we can do this also in northern hemisphere. Actually, I have an example, but I have to switch the screens. Just a second. Okay. All right. So I have to switch the screen to a result that an image I took actually from San Jose, from my balcony with my own telescope. This is the galaxy cluster Abel 2319. This galaxy cluster is actually in Sinus constellation. You know, Sinus constellation is mostly known with the nebula and the NGC 7000 and all these nice areas for H alpha and the different nebula there. But there is a galaxy cluster there, and this galaxy cluster is actually hidden behind the star field. And I was actually surprised that if I take my eye filter, I2 filter, just from the retailer and put on my 61 millimeter Willen optics, I was able to see the galaxies within in between the stars, right? I see this is a galaxy. I plate solve it, and I compare with wide field infrared survey, which is online, and I see the same same galaxy on the same location, right? And the reason why the telescope can see this galaxy is the same reason that I show you with the normal cluster, because when we image with near infrared, it actually cuts off a lot of the stars and still leaves the galaxies on the image. So I actually investigated why is that, and whether it's true for all galaxies. It turns out that when we image with infrared filters, we can see a lot of galaxies on the image, but particularly galaxies which have active core. Means that these galaxies actually have X-ray or black hole in the center of the galaxy, which actually emits strong radiation. And then actually, when we image with eye filters or near infrared filters, we can see them because they're very bright. However, if the galaxy is not active, with not active nucleus or core, it's actually faint on the image. It's not the same result. So there is a trade-off. So we can actually use near infrared filter to see galaxies in the field, but these galaxies are mostly active with active core. And galaxies which don't have actually active core will be fainter. So not all galaxies are responding the same way for the eye filter. Okay, so go back to the slide. Okay. Right. Okay. Can stop sharing first, and now can switch to a different screen. All right, back to presentation. Okay, do you see the slides? Yeah. Okay. All right. Okay, so in the next example, I will show you actually non-galaxy example. And this is actually a recent story, which I actually wanted to show you because it's actually a development story. So there is a star called BX Monoceros, which is currently showing some strange activity. And astronomers, actually, they posted online some results that the activity is high in the recent week and a half. And especially from British Astronomy Association, they actually posted the news and they say, go collect data and see if there is some strange activity continuously going on. So I decided to actually go and investigate and see whether this star has some activity, and to learn more about the star, what is so interesting. And because the recent days it's cloudy in Bay Area, so I had to use again online telescope. So iTelescope network is useful for photometric measurements because many of the telescopes, they have Astroimaging filters like narrowband and LRGB, but also these telescopes are equipped with photometric filters. And that's one of the differences with Telescope Live. Right? Telescope Live, I use Telescope Live, but they use mostly LRGB and narrowband, but they don't have these photometric filters. Well, iTelescope has telescope rigs which with photometric filters and for scientific purpose. And T5 telescope from iTelescope fleet is actually one of the cheapest rigs for scientific astronomy, and many astronomers actually use this rig for measurements. And you can actually have the telescope for $24 an hour, right? Sometimes it's free when the moon is actually bright. iTelescope gives you for free. So last time they didn't even charge me for 1 hour imaging because it's a full moon night. So what is so interesting about this star, Big C Monoceros, right? If you go to Symbiotic, it will tell you that this is a symbiotic star. So, and it has very strange symbols in front. So this is a variable star. When you see V star, that means this star is variable. And it tells you also what type of star it is and what is the physics behind. And when I go to the literature, you see that what is symbiotic star stellar system definition for it. So symbiotic stellar system is actually a binary system of cold red giant star and hot white dwarf. So this is a binary system, and when actually the hot white dwarf pulls material from the red giant, and this material drops on the surface of the white dwarf, we have a thermonuclear flash, and this thermonuclear flash causes a rapid spike of the energy flux, and that's why this star is actually rapidly becoming brighter in the sky. However, these stars stellar systems are very complex because their variability is non-linear. They basically don't have periodicity, very nice periodicity of normal variable stars. They have actually unpredictable flashes, and their behavior is still under investigation, and still to understand what causes this complexity and burst of energy, what kind of reactions are actually happening on the surface of this white dwarf. And this star Big C Monoceros is from this catalog. And it seems that in the recent days it's becoming rapidly brighter because of this accretion disk is actually collapsing on the surface of the white dwarf. And we want to know whether this flash is actually ongoing right now. So I can show you an image of, this is the image of the star from Symbiotic. This is the Deep Digital Sky Survey, right, on the right. And this is the image that I have from iTelescope T5. with the infrared filter. I will show you why I use infrared. I use actually two filters, E2 and B filter, blue filter, because I want to do relative photometry of two filters and measure how the brightness changes with these two filters. And is there any difference between the two? So this is the star in the center. And I want to show you something really cool. Maybe it's a bit white field here. So this is, I actually collected two sets of data from April 13 and April 17. That was 2 days ago. But I want to show you when I compare near infrared filter with blue filter, what is the difference? So this is the B filter, right? And the star that we look for is right in the center here, right? And it seems that around this star, there's nothing interesting, right? So looks like just a bunch of stars, and our object is in the center. But what happens if I switch to I filter, E filter, right? Oh, somebody's here, right? B filter, infrared filter, B filter, infrared filter. All right, so who are these guys? So why they're so bright in infrared, right? And they're almost invisible in blue filter, right? So probably can again switch the screens to show you what is in the Alden web pages. Okay, so this is the Alden web page, and we are on the same location, Big C Bono, and this is a very nice page because it gives you data from various telescopes around the world. You can click here and see all the reference telescope that you can actually compare results with. You can have Deep Sky Survey with color, red, blue, 2 micron, 2 mass telescope, wide field infrared, a bunch of telescopes around. You can actually quickly see the same part of the sky with different wavelengths. And if I click red, I mean color, you see a lot of stars here. Our target star is in the center, and not much around happening, right? You see a bunch of stars, but again, looks like normal sky, right? Now let's go to 2 micron survey. Boom. We have these bright stars on the image, right? And this tool actually gives you ability to understand, to actually see more details of the star just by clicking on it. So who is this guy? Okay, so it says variable star V467 monoceros, type Mira. So, and you can actually click on this, and you can see the details of the star. It's a variable star of Mira Cetus type, and you can actually Google it. Let's see, Mira type. All right. And what it says for this star is that, so these are pulsating stars characterized by very red colors with pulsating period about longer than 100 days. And these are red giants, again. And they expel their outer layers. And they actually become eventually planetary nebula and white dwarf, right? So this explains why we see this this flash, basically. If you look at here, so when I go to again to just color, they disappear, right? They're not there. But if I go to 2 micron, wow. So that means that in 2 micron wavelength, they look bigger. And that corresponds to what this explains, is that these are red giants, and they're pulsating, right? And eventually this will actually be a planetary nebula in the future. So right now what we see here is we see future planetary nebulas. Yeah, these are 4 planetary nebulas in the future. Yeah, so this is what the difference is when we switch to different wavelengths. It actually gives you hidden details of this part of the sky, which are not visible when you go to visible wavelengths, right? So to go back to the measurements that I did. So let's go. Okay, I have to stop sharing from here and go to the sites. All right. So what I see here are the same stars that are actually on our webpage. Right? These are the same guys. These two and this guy. So what I see is consistent with the 2 micron. So basically, my near-infrared image is consistent with what I see from 2 micron. And here is actually the star profile. So I took measurement of the central star, which is our target, big C mono. And I took the profile of the star with I filter and P filter, in near-infrared in blue. And I want to compare the radius in pixels of the star. This is actually needed to actually determine in photometry what will be the numerical aperture that we want to use to measure the energy flux. And you can see that when I click on the star with the mouse, it creates this circle, right? And it measures the profile, and it gives you what is the radius of the object in pixels, and where is the background. The background is this area. So we have 3 numbers, which are 14, 25, and 38. And these numbers are set in the software. I use Astroimaging, right? You put these numbers in the software, and then you can actually click on the star and measure the relative flux. So, but interestingly, what we see is that in I filter, the radius is actually bigger than the B filter. So, and that is normal because this star is actually also red giant, right? With it's a binary system of red giant and white dwarf. So we expect that in I filter it should be wider, right? That's why the radius is 14 pixels, while in blue looks like 6 pixels. Right? So that's expected, and you can use this to set up in the software. And in relative photometry, what we do is we pick up the target star. The target star is in green, and we have reference star. This is in red. So what the software does is it compares the fluxes of the 2 stars and makes calculations, and it gives you the relative flux of the target star versus the reference star. And you do this for multiple stars, not just one, but you have to take actually 4, 5 measurements, 4 different reference stars, even 6 reference stars, collect the data, and then you have to take mean, max, and some statistics to see how this, what are the numbers, right? So let's say I have 5 stars, reference stars, and versus them I want to know the relative flux of this star, the target star, and take mean and error bar. And this is what I get. So basically, with I filter is this blue. It should be opposite, kind of counterintuitive. And B filter is this box. So it's seems that on April 13, right, we see that in blue, we see a bigger energy flux, and I is actually a little bit smaller, right? But that's not the end of the story. I actually took another measurement on April 17, and I see this picture. So basically, this is again the I filter, right? These two boxes, and B filter is this line. So it's actually counterintuitive because on the April 13, I thought probably, in blue looks like it's a little bit brighter than I filter, but actually it's not. It's actually, in I filter, it's actually brighter than blue filter. And because it's actually the steeper, right? And what we see is that this change between April 13 and April 17 is actually bigger than the error bar. So it means that we're taking all the noises and all the errors and all the error bars. This is still actually a little bit higher than what we saw on April 13. Of course, I cannot tell right now that this is a signal. So I want to share first this with professional astronomers and next couple of days. And we'll analyze the results, and if they confirm, will be a good news. Basically, we'll have a flash on the sky in the next days, but we'll see how much brighter it may become. Right? Some people may say they predict it will be as bright as 8 magnitude or maybe 7, which means that we can see this flash with the binocular, but we have to see that. We have to confirm whether this variable star can actually make it to 7 magnitude, right? Or even more. Yeah. Okay. So this kind of measurements are relatively easy. For those of you who actually want to learn more, I can actually give you some literature how to do this photometric measurements. It's basically, you can do it with Astronomy J, which is manual way, but it actually teaches you about the physics, the signals, right? What kind of signals how to process the signal. You can also use Astrometrica, which is another software which does these measurements automatically, but Astrometric is basically automated and is hidden. Basically, you need to learn the literature first and then click the button and it does the measurement. Well, here it's manual, but it's good learning curve to understand all these noises and subtractions and the signal processing. So I would like to end actually with the image that we put on the talk banner, right? This is M106 galaxy with near infrared filter. And the reason I actually took these images with near infrared is because with the current light pollution and the current season, spring, right? The accessible object in the sky are galaxies. And I was curious if I take a bright galaxy and put the near infrared filter, what I can see, right? What details I can actually see in the image. So immediately you can see that we don't see a lot about the outer layers of the outer actually branch of the galaxy. We can see actually the center, but we see details in the structure of the center of the central part of the galaxy. You can see actually these two spirals. You see some interesting objects, and one thing that I notice here is that this is actually not very visible, but you see this small shadow area, which is actually taking off the galaxy plane. So I wanted actually to see whether I can see on the image one of the famous, because this galaxy has two jets coming out of the core, and Francesco was trying actually to, the reason why they created this mega project with the German astronomers is to see those two jets, right? So I'm able to see a little bit of one of the jets in infrared, but I don't see the next one. The next one is somewhere here, the second one. I only see barely the first one, right? And the second one is somewhere here, but it's not visible. So what we can conclude from that little bit, that kind of speculated, is that because this is near infrared, and when we image the sky in near infrared, we're actually looking cooler objects, which are relatively cool to other objects. That's why we see this star a little bit wider, because it's actually cooler, red giant, right? And that's why it's with a greater radius of the profile. So something similar happened here. It seems that because we don't see the second jet here, we see in infrared a little bit of the first jet around that area. Means that this first jet is probably a little bit cooler than the first one, right? So we start seeing these little bit temperature differences. But of course, this is just a rough estimate, right? It has to take more images, and as Paul said, we have to actually take care of this water vapors and all these corrections before we draw any conclusions. But yeah, the first data actually show that we can see in near infrared one of these jets here, a little bit. And actually, this is not with 200 hours exposure. I use probably 2-3 hours, right? Each frame is actually 600 seconds, just normal exposure time, which we typically use for narrowband. I use narrowband strategy for this kind of objects. I use 600 seconds exposure for near infrared, even at bright moon sky, and I still see the galaxy here, right, on the image. So that's for future. So that's an ongoing project, whether I can see both jets on the image with different filters. Still experimenting, so we'll see what will be the result. So that's it. If you have questions.
All right, thank you very much.
Welcome.
Are there questions from the audience? I know there have been several asked during the talk, but. Well, I guess we'll have to read up. Can you put some reference? Can you mail out reply all, I guess, to my talk announcement with any references? You know, I found that I guess you could also put comments in the meetup, but I think if you just, you know, mail it out.
Yeah, I will put actually a reference to how I did this measurement, so it can, if somebody wants to repeat. Yeah.
All right.
Nikola, sorry, can you say again the parameter of your last image? You're talking about 600 seconds, but how many subs?
So I took about more than 20 subs. Actually, for actually more than 30 subs, but in different nights. So I had one night, second night, third night, and then accumulated together. With each frame is 600 seconds. Okay.
Okay.
Yeah. Because I wanted to experiment how far I can go with the exposure with this filter, just by punching numbers on Nina and see how far I can go. But if I have to be scientific, right, I have to use Francesco's method. So he has a formula which gives you the gain and exposure time for each filter for specific camera, right? So that's what I'm going to do next night when I have opportunity to image.
To use the nomogram and calculated the ideal exposure. Okay.
Yes, exactly. Yeah, and just want to compare whether I really get optimal exposure and gain for these images. Yeah.
Makes sense. Yeah. Thank you.
Welcome.
All right. Any other questions? Okay,
Nikola,
go ahead.
is your near infrared, is that the 805 nanometer? 806 rather?
Yeah, 806. Yes.
806 nanometer. Okay.
Yeah.
Got it. Thank you.
Yeah. So I haven't tried with further. I still need to purchase it because recently we have cloudy weather, and I can sort of hold until the weather gets better, and after that I can switch to Z filter and see if there is an impact.
And
yeah.
What was the camera that you used?
So for this one, I use Orion G3 CCD. It's very beginner level camera, but it's already, I already replaced it with ZWO. So the old CCD will go to different rig, and they continue measurements there. But the current rig has already ZWO. STI.
Okay.
Yeah.
And the CCD camera that you used was cooled or not?
Cooled, yeah, cooled. It's actually -10 C.
Okay.
Because it cannot go below that because it has weird noises, dark current, which I cannot remove from the image easily.
Okay.
Yeah.
Okay. Yeah, I'm interested in the result of the CMOS because, of course, I have the CMOS, not the CCD.
Yeah, that's basically the next evening that we have clear weather. I can. It's already set up. I just wait the clouds to go away.
Yeah.
And take images. Yeah.
Okay.
I can show you. Let me finish with that. Okay. Go back to Alden. That will be the end of the talk. Let's see where it is. Okay. Share. All right. So again, going to show you Z filter, right? But I have to go to one of the galactic clusters. Let's say. Double clusters. Let's see this one. All right. Okay, this is in color, right? Digital Sky Survey, and now I'm going to switch to this filter, which is Pan Stars Z. Let's see if we can get something. See? Yeah. See how much more details we see with this filter. Yeah. That's why I want to see with to buy this Z filter and experiment with it.
Yeah, but I think that at that point, the sensibility of the sensor will be important.
Yeah,
I mean,
because
the Z,
exactly.
if I understood, start more or less like the eye filter, but go on long wavelength. No?
Yes, and also we some cameras are actually dropping the efficiency of the signal when you go to very deep infrared, right? So actually the curve of the efficiency is dropping quickly.
Yeah.
So I have a very expensive CCD camera, which is Apugi. I haven't set up yet because I initially wanted this big CCD camera for normal imaging with H alpha Note 3, but it's too heavy for my rig. So yeah, I cannot balance the weight of the scope with respect to the mount because the camera is too big, too heavy. So I will repurpose it for scientific, but I need bigger mount for that. So it's I need bigger mount and better tracking in order to install this camera. It's actually full frame and it's actually for scientific purpose, but it's heavy.
Yeah, I can imagine.
Yeah.
Yeah, I'm checking in this moment the chart for the relatively sensibility, the QE graph, but it's stopped at 800 nanometer. So,
yeah. And how quickly it goes down to zero, right? After that.
Yeah, and 800 nanometer is already 35 relative output level respect of the 100% of more or less 520 nanometers. So
Yeah,
it's
that means
going
that
down.
we have to push the exposure time further.
Okay.
All right.
All right, well, I say we call it a day.
Yep.
It's okay, everybody, thank you very much. Unmute and applaud. And thank you very much, Nikola.
Thank you, Nikola. That was great. Very
Thank you.
interesting.
Thank you. Thank you. Welcome.
Thank you, Nikola.
To give me some idea.
We can experiment together, right?
Yeah.
Yeah.
Yeah, because